In the fourth part of the Opus Maius, in the fourth distinction, one finds a short chapter devoted to a problem concerning the motion of the scale. In this talk, I consider the problem which Bacon tries to solve, the way he solved it, and the context in which he discussed it. I conclude by a few remarks on Bacon's use of geometrical demonstrations in physics. So I begin with an outline of the state of the science of weights, what we call today statics, but with the science of weights in the 30th century. So the medieval Latins of the 30th century inherited from the Greeks and Muslims a few principles of statics, the most prominent of which was the law of the lever. Archimedes provided the proof of the law of the lever, namely that there is an inverse proportion between the weight and the length of the arm of the lever on which the respective weights are suspended. Archimedes' demonstrations were wholly geometrical in character. The theorems were inferred from postulates or axioms in an Euclidean manner. In 1269, William of Moerbeke translated Archimedes' writing into Latin. So they were not available at the time when Bacon wrote his Opus Maius, and they were also not available to Jordanus. I will speak about him in a minute. But apparently they knew about them in other ways. Another version of the law of the lever appears in a text titled Mechanical Problems, attributed to Aristotle, but probably composed by a later author. It is not certain, though, that this text was available in the 30th century. The version of the law of the lever in this text states that the effective weight on a balance or lever increases proportionally with its distance from the fulcrum, because the distance from the fulcrum endows it a greater velocity, because it traverses a larger arc in the same time. The effective weight is increased by the amount of the velocity, namely by the size of the arc. I'm not going to survey all the sources. There were a few others, just the two main ones. So in the 30th century, there's a new series of tracts on statical issues, which is called in Latin Scientia de Ponderibus. They were composed, and the most important of which were three, and they were all ascribed to Jordanus de Nemore and his school. Jordanus reworked the material of the Hellenistic mechanical tradition, and in so doing consolidated the union of Aristotelian dynamics with Archimedean mathematical statics. There are three texts associated with Jordanus, and you have them listed here. One is the Elementa, and second is the De Ratione. This is the shortened version. And the third is Liber Jordani de Ponderibus. So of these, the Elementa and the De Ratione Ponderis are probably authentic. They're probably by Jordanus. There was an argument between Duhem and then Clagett and Moody about the authenticity of these works, but you know, I accept what Clagett and Moody propose. And apparently the De Ponderibus was written by one of his students or disciples. In these two books, Jordanus touches upon the three most pivotal statical principles besides the law of the lever, namely the principle of the inclined plane, the principle of the composition of forces, and the principle of virtual displacement. I'll just say virtual displacement is a modern term. It was not used by the medievals, and apparently you can say that they had, I will mention it a few times in my talk, but you can deduce or the principle of virtual displacement from what they did, but that was not their principle. It's when we as moderns look at them, we can recognize that the germs are there for this principle. So an important principle from the Mechanica ascribed to Aristotle, called Aristotle's axiom, states that if a certain motive power moved a certain body with a certain velocity, then twice the motive power will move the same body with twice that velocity. That's a dynamic principle, and in statical terms, it means that the motive power is equal to the weight of the moved body times the distance through which it moved. In Elementa, Giordano gave a formal geometrical proof for this principle, beginning with Aristotle's axiom that equal weights at equal distances from the fulcrum were in equilibrium. In the course of the proof, he made use of what he called the axiom of what is called the axiom of Jordanus, and you have it here. Namely that the motive power, which can lift a given weight a certain height, can lift a weight k times heavier to 1 divided by k times the height. This is the germ of what would be later called the principle of virtual displacement. So who was Jordanus? Jordanus de Nemore. We know he was a capable mathematician, apparently of an Italian origin, who composed treatises on algebra, arithmetic, and geometry. He wrote the De Numeris Datis, which was the first treatise on advanced algebra composed in Western Europe, and the Demonstratio de Plana Spera on stereographic projection. It has been suggested that he may be identified with Jordanus Saxo, who was the second Master General of the Dominican Order, but the evidence for this are slim. If indeed he was the Dominican Master General, then he died in 1237, and then his work should be dated to before 1220. Another possibility, though, is that Jordanus was a teacher of mathematics at the arts faculty in Toulouse, and that arts faculty was established in 1229. And if this is the case, then his works may have been written considerably later than 1220, and the composition may have extended over a considerable period of time. In any event, it is certain that his works were compiled before 1260. Now, if the latter option stand, namely that he was a teacher at Toulouse, it has been suggested in a paper from 1988 by Jens, I don't know how to spell out this name correctly, Jens Hirop, something like that, that Bacon and Jordanus may have met in the 1240s in Paris, while Bacon was teaching there. On this suggestion, Bacon may have had a close contact with Jordanus and his circle, although he was not an actual member of that circle. Okay, and that's important because you'll see, because of what I'm about to say in the as the concluding remarks. Jordanus is considered to be very important in the history of mechanics, and his works, apparently he was not that well, not very well recognized in the 13th century, but in the 15th century, Balesius of Parma, he summarized his works, and apparently Leonardo da Vinci used them. So, before I discuss Bacon's problem of the scale, let us clarify an important concept which Bacon took from Jordanus, namely the concept of positional gravity, gravitas secundum situm. This concept is introduced in both the Elementa and the Ratione Ponderis and was not found in earlier literature. According to this concept, a weight is heavier positionally when at a given position, its path of descent is less oblique. A more oblique descent is one in which, for a given distance, there is a smaller component of the vertical. And I will show you soon the diagram so it will become clearer. This means that the force along an oblique path is inversely proportional to the obliqueness, while obliqueness is measured by the ratio of a given segment of the oblique path to the amount of the vertical intercepted by that path. I want to see just a minute. Oh, where is it? Yeah, okay, positional gravity. In modern terms, we would say that when the oblique path is a straight line, then the force F along the oblique path is computed thus: F equals W sinus alpha or A. W is the free weight and A is the angle of inclination of the oblique path. When the path is arced, the positional gravity of effective weight is measured by taking an arbitrary segment of the path of the possible descent or ascent of a weight and determining its projection on the vertical. The larger the vertical projection is in relation to the length of the trajectory, the heavier is the positional gravity. So now, okay, now let's see what is Bacon doing with the scales. So he thinks there's a problem. He thinks that there's a problem with I'll spell out the problem in a minute, and he's trying to solve it by using Jordanus. But he starts out with some definitions, okay, of some basic concepts that he'll need for later on. And it is important how he begins this chapter. It's chapter 16. So he declares that he wants to disclose, and there's a quote, the potency of geometry in motion. Okay, and that will be the main theme of the talk, the geometry of motions. Namely, he wants to demonstrate how effective geometry is for the study of motion. So he started out from a sort of evident theorem, namely that two beams of equal length carrying equal weight will be in equilibrium. And if disturbed, they will return to horizontal position. So he defines D. You can see that there's the drawing taken from the Opus Maius, the drawing taken from Jordanus. They are pretty similar. So D is the center of revolution. Okay, A and B is the diameter, which is in fact the beam, the two arms of the scale. And CD is actually this is where the balance is suspended from. Okay, it's a balance that is suspended from above. Okay. So he defined the center of revolution around which the equal arms of the scale form a circle. And he added the same diagram which appeared in the Elementa and in the Ratione Ponderibus. It's about the same, slight differences, they're not important. Okay, so he's obviously, and you'll see in a minute, he's obviously relying on Jordanus. He's also saying so. And you can see now the diagrams by Bacon and by Jordanus. Okay, the direction is different, the letters are different, but it's practically the same diagram. So we will get to this diagram in a minute. Then Bacon moved to the problem that intrigued him. And what was that problem? So Bacon noted that the velocity, it was not just him, it was an accepted principle. Bacon noted that the velocity of a free-falling body increases as it ascends. The velocity of a falling body is also, so it was held, proportional to its weight. Hence, supposedly, the more the body descends, its velocity increases, and therefore the greater is its weight. So the more a body is getting closer to the center of Earth or of the universe, it's supposed to weight more, right? Which is, and the problem is this. So if we have a scale with two arms, the two arms are equal in length and they carry equal weights, they will be in balance. But what happens if one presses one side of the balance, okay? And Bacon says, okay, according to the accepted principles, the heavier arm becomes heavier because it is closer to the center of the universe. But this contradicts what we see from experience, okay? Because from our experience shows us that the balance would at some point return, the scale would return to balance. So how can that work together? So that's the problem. And Bacon, he treated in the Communia Naturalia, he tried to give an explanation to the why a body accelerates. Of course, he doesn't speak about on acceleration because that's a concept that was not familiar to him. But why does the velocity of a free falling body intensifies when it gets closer to the center of Earth? And he gave it a solution in terms of power of forces, of virtues. It was not there was no geometry there, no diagrams. He says that the virtus internal to the falling body is always operative, but there's also the virtus of natural place, and the virtus of natural place starts to work only from a certain distance, and then when the body approaches that certain distance, then it is moved not only by the internal virtus of the moving body, but also by the external virtus of the natural place, and that's what intensifies its motion. So that was a very important principle for Bacon. So Bacon deduced that if one would depress one arm of a balanced scale, namely one in which both arms are of the same length and carry the same weight, then the lower arm will become heavier. The higher arm will become lighter, balance will be lost, and the two arms will not return to horizontal position. However, he concluded this is clearly contrary to experience, and it is contrary to what Jordanus says. He then, in order to solve this difficulty, he appealed to the concept of positional gravity, taken from Jordanus to resolve this difficulty. The path drawn from the lower weight to the vertical line, passing through the point of revolution to the center of the universe, would be less oblique than the path drawn from the higher weight. A conclusion of this kind, he states, requires a figure. And this is the figure he draws. So basically, what he's showing us is this. So he doesn't say that, but I found it in Jordanus. So he draws parallel. So this is the original position of the scale. Do you see my arrow? Okay, and so you press the scale on P. Okay, so P is lower now, and T is the other arm. It gets higher. Okay, so you see here parallel lines. Okay, so you draw parallel lines to the diameter, to the horizontal diameter, and you take equal segments of the arcs. So the arcs on the circle are equal to one another. Okay, but the more you approach to the edge of the circle, the segments that these parallel lines cut from the vertical, okay, CD is the vertical, they become smaller. Okay, the more you get close to the original position of the scale, these segments are larger. Okay, so now what happens is if you press P, then if P wants to keep descending, okay, to get to H, the segment of the vertical it would pass would be smaller than the segment of the vertical which T in its descension to A would pass. Okay, so because this segment, because it's further away from the center, okay, is smaller than this segment. Okay, that's and therefore T is heavier because its velocity its velocity is greater. Okay, because it passes in the same time more of the vertical. Okay, that's the idea, and that's pretty much the idea of Jordanus as well. So so Bacon explained that the lines parallel to the scale cut unequal segments from the vertical. The nearest parallel to the scale will cut the larger segments on both sides, and the farther one will cut smaller segments as they near the edges. He examined what would happen if P would descend to H, and what would happen if T would descend to A. Sorry, what would happen if P would descend to H? Wait a minute, where are we? P, P would descend to H, and what would happen if T would descend to A? The part of the diameter DC traversed by T would be greater, so that's the diameter DC, would be greater than the part of the diameter traversed by P. Therefore, T would have a heavier positional weight than P. Bacon added the following figure, which is not found anywhere in Jordanus, and I want to show you. This is he didn't take from Jordanus, okay? And he adds this because he thinks that what Jordanus was saying is actually not enough. So he thinks you need some more considerations here. So it's a sort of an alternative explanation. And again, you have the T and the P here, right? It's the same points which we have seen before. And he drew the obliques from both to the center of the universe, okay? And he writes that while T naturally tends to fall back toward the center of the universe, P, and by the way, you can see that T, I think it's O here, I'm not sure, it's cut, is more oblique than PO, okay? So while T naturally tends to fall back towards the center of the universe, P, on account of the bending of the circle, tends away from the center. And from this reason, it would be less heavy. So I find it very unconvincing because T also doesn't move in a straight line. It also moves in a circle, on an arc, but in principle, P should have been heavier since it is closer to the center. But since its trajectory is not a straight line, but the curved circumference of the circle, which is a less direct course than T, T becomes in fact heavier. The two reasons given for weight here overcome the reason for P being heavier. Okay, so the two reasons are their explanation he took from Jordanus and the explanation he added on his own. So the two reasons given for weight here overcome the reason for P being heavier. P is still supposed to be heavier, okay? But the weight added to P becomes, according to Bacon, insensible. So it's like a feather. It's like compared to the other forces at work, it's too small. Okay. The additional acquired weight is too small to have an effect. When the weights keep oscillating before they reach the final equilibrium, it is not due to the nature of the weights, but to another cause, he says. That's the impact of the particles of the air which keep vibrating for a while. Okay, so you see, the interesting thing is we have both, we have some physical considerations and we have some geometrical considerations here. They are sort of mixed together. I don't know if it's, I have an explanation here of Jordanus's treatment of the balance, but Bacon is pretty much, he gives an appropriate presentation of what Jordanus is saying. Okay, so I don't think I need to repeat that. So what can we make of this? So I have some thoughts, some things we can learn about this whole this small chapter regarding Bacon. So Although, as we can see, Bacon presented Jordanus's geometrical reasoning appropriately, he thought it stood in contradiction to physical principles of an Aristotelian origin. He clung to the idea that weight increases with proximity to the center and could not recognize the difference between a constrained static system and a dynamic one. His attempt to settle the apparent contradiction indicates that he was looking for a universal theory of gravitation, which I have to grant him that at least. At the end of the day, however, he favored the geometrical argument over the physical one, but without completely dismissing the latter. So one can appreciate his conception of natural motion and natural processes in general as an outcome of a play of forces driving in contrary directions. I think it can be safely inferred that Bacon made no significant contribution to the theory of weights. There are, however, several points here that are nevertheless worth mentioning. So, one, despite the shortcomings of his grasps of the theory proposed by Jordanus, one can acknowledge that Bacon was in a position to identify and appreciate Jordanus's achievements. And if anyone knows differently, I would be happy if you would tell me, because I did a very shallow search. And I don't know if Albert the Great and Thomas Aquinas mentioned Jordanus. I suspect they're not, but I'm not 100% sure about that. So I think that's in favor of Bacon to say that he recognized, I mean, he was curious enough to know what other people were working on around him, and people who work on science and math. And he did try to integrate their findings in his own synthesis. Okay, so he wasn't especially capable in doing that, but at least he tried. His belief that science is a joint human enterprise did not remain at the level of empty declarations. He put it to practice. Okay, and this can be seen also in how he treats Peregrinus with a compass, yeah, with a magnet, sorry. So that's one point. Second point, the medieval concept of positional gravity exemplified the idea of the resolution of a force into various components. Jordanus showed that the motive power by which the body was moved could be deassociated into two: the natural gravity downwards towards the center and a violent horizontal force constraining the weight to move along the curve instead of descending vertically. He called the component of gravity acting along the trajectory positional gravity, and showed that the more the trajectory is oblique, the smaller was this component. Bacon adopted in full the idea of motion as resulting from a composition of forces and applied it in various contexts. One example is found right before the chapter on the motion of the scales, namely chapter 15. Here, Bacon demonstrated geometrically that the natural movement of a triangular body downward involves strain and therefore produces heat. So the common notion was that only violent motion produces heat. Bacon is showing here that also natural motion produces heat. And you can see that's his own figure. Okay, that's his own. You can see it's like sort of primitive, but I don't think he took that. I mean, since he doesn't mention any name from which he took it. He appealed to a geometrical diagram to show that bodies which do not fall on the line perpendicular to the center of Earth must deviate towards the center and move diagonally. The diagonal motion is the result of two motive forces which draw the body in opposite directions. The natural force of the heavy body draws it downward, while the force of strain tends upward. The consequence of these pulls is a certain verification of that body, and verification is an immediate disposition to heat, Bacon said. Historically, the analytic intuitions of this kind led to the discovery of many general scientific principles. So I think this is an important methodological point about what Bacon is doing. Third point. So Bacon actually appeals to the Jordanus in one other instance. It's in chapter 11 of the same distinction. And that is done within the context of a third geometrical analysis of motion. In his book on the triangles, Liber de Triangulis, Jordanus addressed the ratio of arcs and plane segments in different circles. Bacon relied on theorem number 28 from this book for his proof of the cause of the phenomena of the contraction of water as they get closer to the center of the universe. He argued that if we were to place two cups, one at a higher place, such as a balcony, and another in a lower place, such as a cellar, and then fill them out with water, the water will form itself, and that's a quote, the water will form itself into a smaller and larger sphere with respect to the center of the earth. And you can see here the two spheres. The water's surface of the higher cup will be a portion of a sphere more distant from the center of the earth, and therefore larger than the surface of the water in the lower cup. Okay, so this is where the lower cup is, and I'll show you. This is the lower cup, this is a higher cup. So you see it's the same, the cord is of the same length, okay? But the lower one cuts a larger arc from the smaller circle, and the higher one catches a smaller arc, cuts a smaller arc. So the water's surface of the higher cup will be a portion of a sphere more distant from the center of the earth, and therefore larger than the surface of the water in the lower cup. The diameter associated with each cup will then cut an equal chord, assuming the cups are equal, of each sphere. However, the proportions between the chords and the spheres will be different. The chord of the higher cup will form a smaller part relative to the larger sphere, while the chord of the lower cup will be relatively larger. As a consequence, the water's surface of the two cups will differ. The smaller sphere of the lower cup will result in higher surface, while the higher cup's surface will be lower. Given this situation, Bacon inferred, the lower cup can contain more water than the higher one, since the same amount of water will require less space, or in other words, the water in the lower cup will contract. Bacon wrote, by the 28th proposition in Jordan's triangles, in unequal circles, the same chord cuts from the larger circle the smaller portion, and from the smaller circle the larger portion, and the same is true of spheres. So it seems that all the three diagrams of motions in the fourth part of the Opus Maius, and these are the scales, and this one and the previous one on the heat caused by free fall motion, they were all in some way inspired by Jordanus. And last remark that I have to make, in distinction 4 of the fourth part of the Opus Maius, Bacon examined the different aspects of the relations between matter and quantity. Now I'll look at the whole distinction. So far, I only did 3 chapters in that distinction. There are 16 chapters there. So Bacon examined the different aspects of the relations between matter and quantity, or in other words, between the disciplines of physics and math. He considered the relation between physical and mathematical lines, the unity of time, and the geometrical shapes of the elements and the universe. He then selected a series of specific case studies, which he analyzed geometrically. In all these case studies, geometrical and physical considerations are used, thereby creating the impression that the two types of considerations are in fact inseparable. The case studies include the law of the gravity of water, the 2 cups experiment, the strain caused by the natural motion of a free-falling body, and the oscillation of the scale. It is obvious that Bacon placed much emphasis on geometrical considerations in optics. We know that. And we know that his source when it came to this discipline was Alhazen. The significance he ascribed to geometrical demonstrations of motion is less well known. I suggest that while in his geometry of optics he was very influenced, or even derived it from Alhazen, his geometry of motion followed to a large extent that of Jordanus. And so I think Jordanos was very important for Bacon. And I admit the diagrams that Bacon draws are not very impressive. They're pretty even primitive, I would say. His more sophisticated diagrams are definitely the optical ones, or as we have seen here, the one that he actually took, borrowed from Jordanos. Yeah, but nevertheless, I think the attempt or the idea that motion can be described by diagrams and forces can be described by physical forces, not just in optics. So I think that's important. So thank you.